Okay, good morning. Ah, so tinitignan ko yung ano niyo 'no, yung progress niyo on in Uvle so far. Ah, konti pa lang yung nakaabot sa strain. So, si nabasa niyo na ba siya? At least strain, tensor? Please click yes or no kung nabasa niyo. So please 'no, at least mabasa before for our synchronous meeting para maging kasi at first glance yung mga topics sa C18 is really hard. So I at least scan it as note some misunderstandings and list the questions that you want to ask and and then try to read it. Okay? So anyway, um, let's discuss this and I hope maging productive still yung ating synchronous meeting. Yan. So what we're going to discuss now is strain. So review lang, what we have discussed so far is continuum mechanics and indicial notation. So I hope that you know how to expand indicial notations. You know what Kronecker delta is, what permutation symbol is, and you know how to you know what dummy indices and free indices are. Okay? So yun lang. Next we discussed tensors. So I hope that by now um, you have an idea of how of what a tensor is. Basically, a tensor is a mathematical object which obeys some transformation laws. Okay, so for example, the degrees of tensor. I hope you know those things. 0-degree tensor is a scalar. First degree tensor is a vector, and a second degree tensor can be represented by a matrix. Okay? And we discuss stress. So we have defined stress in a way in a continuum mechanics notation. Okay? And we have determined that stress is actually a second order tensor which obeys second order tensor transformation laws. Ayan. Now we move on to strain. What is strain? So, alam niyo naman ang strain, it is the percentage of elongation. Ayan, from your ES 102. So the objectives for today is to describe motion, ayan, and displacement dapat dun. Okay? Define the displacement gradient and then define what an infinitesimal strain tensor is and discuss how strain transforms. So ano nga ba ang strain? Ano yung degree of it as a tensor? Okay? And of course discuss principal strains and its corresponding directions. Okay, here. In this slide we have this object right here, okay? And we call it object and it has a point P, yung blue dot na yon, point P na yon, which is has a coordinate, has a distance from the origin O, x. Okay, yun yung distance niya. Distance x from the origin O. Let's call this initial point, okay, the reference configuration. So ito yung before siya mag-deform, okay? Now, after deformation, okay, nandito na siya. And as you can see, nagbago yung configuration niya. And now, point P is at distance small x from point O. We call this kappa as the deformed configuration. Okay? Convention lang yan. And again, we have this defined by axis 1 and 2. So, madali na yan. Now, we have two ways on how to describe what happened. Okay? The first way is to describe it in a Lagrangian way. Okay? Or we sometimes call this the material description. Lagrangian description. Okay? So, what is this? Here, we describe the distance small x or the deformed distance of point P in terms of the reference configuration. Okay? So we call here x as the material coordinates. And if, for example, we have a sort of property of the point P. For example, temperature, kunwari. Temperature. So we can describe the temperature in terms of the material coordinates. So, ang nangyari is that even though nag-deform itong object natin, we still use the coordinate system, okay, based on the undeformed configuration or the reference configuration. Gets ba? Ito basically yung ginagawa nyo for the past courses nyo on mechanics. We'll see later, okay? May comparison naman tayo kung medyo malabo. But ganun siya, okay? Nire-retain mo yung coordinates based on the reference configuration. On the other hand, we have this spatial or what we call the Eulerian description. Okay? Eulerian. Dito naman, yung configuration mo, yung coordinates mo, will follow the deformed, okay, configuration. Okay? So, yung itong reference configuration x, okay, is a function, okay, is a function of the spatial coordinates or the coordinates at this configuration, and also the property of point P. For example, this is a temperature phi, will be a property of will be a function of the spatial coordinates. So ngayon, sinusundan mo naman yung configuration ng object mo based on its deformation. Malinaw ba? Malabo, no? Actually, nalabuan din ako dito nung tinitake ko tong course na to. But I hope this next slide, this one, helps. Okay? So what happens here? What happens? So this object right here, at time equals 0, this is the reference configuration. Okay? This is the reference configuration. And then at time 1, time 2, time 3, and time 4, it deforms. Okay? Humahaba siya. So tingnan natin kung ano yung material and spatial coordinates. Okay? So here at time equals 0, the spatial the material coordinates muna. The material coordinates is 0, 1, 2. Okay? So 0 doon sa left end, 1 doon sa middle, and 2 doon sa 2 doon sa right end. Okay? After deforming, anong nangyari doon sa material coordinates? It still stays the same, no? 0 doon sa left end, 1 doon sa middle end, middle point, and then 2 doon sa right end. And as you can see, doon din sa 2, okay, at time equals 2, ano nangyari? Anong nangyari? 0 doon sa left end, 1 doon sa middle, 2. So, anong nangyari doon sa material coordinates? It adjusts to the material. Kaya siya tinatawag na material coordinates. Okay ba? Okay ba yung malinaw? Pa-click na lang ng yes kung malinaw or hindi malinaw. Okay. Ngayon, we discuss spatial coordinates. Sa spatial coordinates naman, ang nangyayari is here, 0, 1, 2, okay? Pagka nag-deform na siya at time equals 1, anong nangyari? Na-retain itong coordinates na ito. So, hindi siya nag-a-adjust dun sa material. It stays with the space. Okay? Kaya siya tinawag na spatial coordinates. It is fixed on space. Yan. Okay? So, for example, we have a property. For example, this temperature, kunwari ito. What do we see? What do we see? Of course, for example, we look at this. We look at the middle point, for example. We look at the middle point. The temperature at the middle point daw, at time equals 0, is of course 0. And 0 din sa spatial. What happens kapag time equals 1? Okay? Pag time equals 1, yung temperature, kapag material coordinates yung ginamit mo, will be described by this formula. Okay? So 2 times 1 squared times x, which is equal to 1 kasi nasa middle point, 1. So 2 times 1 times 1 times 1, so 2. Yan, tama. Now, how will you describe this? How will you describe this? How will you describe the temperature at this point? Yan, using spatial coordinates. So dapat, ang gagamitin mong x is about 1.5 siguro ito. Okay? And to do that, you need to substitute the small x in this equation. Okay, may question tayo. Sir, if material coordinates x equals 1 lagi sa midpoint? Yes. So yung coordinates natin, it adjusts to the material. Okay? Lagi. So hindi nagbabago kahit na mag-deform yung material mo, nag-a-adjust yung coordinates mo with the material. Okay? So ayan siya. So that is what happens. And here, ayan o, meron kang she. Tama ba? Tama ba? Tama ba yung ano ko? Greek letter ko. She. She function of x t is this one. Okay? Hi sir, pa-define po ulit ng variables. Okay, sige. Balik tayo sa, ayan. Okay, yung big X, yun yung material coordinates. Okay, big X. So doon yung reference configuration mo. Yung small x is the spatial coordinates. Okay? Or the coordinates that is fixed on space. Okay. I think, wait lang. I'll Wait lang just give me a minute. So yeah, here is a visualization of what happens, um, what I'm saying, no? So comparison of Lagrangian and Eulerian description. So yung material coordinates is the green one, okay? And the spatial coordinates is the red one. Okay? So what you are using kapag, so imagine niyo that you are this particle or this particle, pag material coordinates yung ginagamit nyo, ang ibig sabihin, parang or Lagrangian coordinates, nakasakay ka doon sa point mo. Okay? At hindi nagbabago yung coordinates mo. Sinusundan mo lang yung coordinates ng point mo. Pag Eulerian coordinates, you are fixed in an origin, for example, okay? You're fixed here, and then you're just observing the particle from this point. So, from this space. Okay, so fixed ka. Ayan. So, I hope medyo gets nyo na yung description niya. So, saan ginagamit, mostly, ginagamit ang Lagrangian coordinates for solid mechanics, no? So, yun yung mostly na ginagamit natin where we're defining stress, defining strains, yung engineering stress and strains that we use. But for example, if you're studying fluids, it might be better, or it might be more it might be easier to use the Eulerian coordinates. Kaya kung nag-take na kayo ng fluid mechanics, um, you might hear of Eulerian or Eulerian mechanics. Mas ginagamit siya doon sa sa domain na yon. Okay? Because it's easier. Why is it easier kapag fluid mechanics? Wait lang. Why pag solid mechanics, for example, if you're studying stress and strains, why is it easier to use the material coordinates? Yes, okay, tama. No, so sa solid mechanics kasi you can pinpoint, okay? You can mark the point in which you are observing. Okay? For fluid mechanics, ang problem is that you cannot mark the point, right? Hindi mo mark yung certain fluid particle. Very erratic siya, di ba? Di-disperse agad siya. So, easier if you have, tama nga yung sinabi sa chat, na ang ginagamit sa fluid mechanics is that you have a control volume and then you observe everything that happens in that control volume and then infer some observations and explain what happens in that control volume as opposed to Lagrangian mechanics, okay, where you pinpoint the point, okay, and then observe everything that happens to that point only. Okay. So I hope that medyo nagets nyo na sana yung difference nila. Okay. Now, yeah, here is an example. Okay. So here, if we want to get the property T, I guess this is temperature, T, big T of the point X, material coordinate X equals 2 at time equals 3. So ano yan? This is the end. No? X equals 2 is the end. This one. Then we just substitute T. Okay? So 2 times T squared X equals 36. Now, how do we point this out if we use, how do we define this if we use spatial coordinates? That is small x equals 5. Okay? Small x equals 5. Which is here. Small x equals 5. And then we find out that it is still equal to 36 because we're defining the same point. Okay? So those are the two descriptions of positions that you may want to know, especially if you want to specialize in a field related to this. Okay. Now, very important in describing strains, okay, is that we define the displacement. Okay, so we have defined two descriptions of motion. Now we define that motion, okay, define the displacement in terms of those two descriptions. So what is displacement? Displacement is simply the difference, yan, the difference, wait lang, ano nangyari? So this is the reference configuration, this is the deformed configuration. What happened to P is that P moved here. So the displacement is the difference between the coordinate here and the coordinate here. But then we defined capital X to be the initial position of P and small x as the deformed position of P. Thus, the displacement is just the difference of these two vectors. Okay? So, small x minus big X. So, yun lang. Now, in material description, of course, this is small x, okay, is defined by a function xi, okay, function xi that is a function of big X and T. Okay? So lahat ito will just have the material coordinate big X. Okay. Now what is the spatial description? Ito naman yung magpapalit. So inverse xi, okay? Function of small x and t. So everything here will be in terms of the spatial coordinate small x. Okay pa tayo? Again, this now, since we're discussing solid mechanics, we will mostly, okay, use this material description. And so here, just to show again what material and spatial or Lagrangian or Eulerian description is, we define the displacement displacement at of 1 point. For example, this endpoint here at t equals 3. So what is the displacement of this point here from the reference configuration? Okay? So ang displacement lang is, pag titignan lang natin, 1, 2, 3. Okay? So here, stated 3. Visually, no? 1, 2, 3. So the formula is this. We know that x, the function xi is x equals x, big X times 1 plus 0.5t. So we just substitute it. Okay? And for spatial coordinates, of course, babaliktarin mo to, i-inverse mo to get the inverse xi function. Yan. Note this one. Sorry, hindi kita. I think, yan, kita na. Okay, so note that xi, the inverse xi function is x over 1 plus 0.5t. Thus, the spatial description of the displacement is small x minus inverse xi function. And we notice that both gives the same answer. So it's equal to 3. Okay. Now, we defined what a displacement gradient is. So from the name itself, displacement gradient, we this is how does the displacement change, okay, along the length, okay? How does the displacement change along the length? So we notice, for example, this d capital X or d big X is the distance between these points P and Q. Okay? After deforming, the distance is now d small x. Okay. Now, say that delta U is how, so is a factor, okay, of deformation. Ayan. So this delta Ux is what we call the displacement gradient, or how much does the distance change along the length. Okay? And suppose that these are very small deformation, ayan, we just express it in terms of derivative. Get naman ito, no? dx equals, of course, this deform x is equal to dx plus some factor delta u dx. Okay. And then just rearranging this, we get this one. Gets? Wait lang. And now this is the description of the displacement gradient. So as you can see, this is how the displacement change over the material coordinates x. So as I've said earlier, okay, what we use in solid mechanics is mostly the material or the Lagrangian mechanics. Okay. Now, let's look at an example. Okay. So here we have x1 equals big X1 plus 0.5 big X2 plus 3.5. x2 equals big X2 plus 4 and small x3 is equal to big X3. Okay, and then what we'll do here is to define the displacement function, okay? Displacement function in terms of the material description, okay? Using the material description since we are in solid mechanics. Ayan, so U1 equals, well, so here, this is the Xi functions, no? These are the Xi functions. So we just substitute U1 equals, gets ba kung ano nangyayari dito? So this one, x1 plus 0.5, x2 plus 3.5 minus x. 1. Okay? So nawala yung x1. Here, 4 na lang natira. Here, x3 minus x3 is 0. So gets naman yung nangyari? Gets ba? Could you click yes kung gets? Gets naman. Okay, so gets naman. Ayan. So now this is the displacement gradient. So delta U, okay? Delta U is just, and balik tayo dun sa description. Row, okay? Row yung I, column yung J. Okay, take note. Row yung I, column yung J. So here, everything row 1, row 2, row 3. Then column yung J, column 1, column 2, column 3. So it's just a matter of substitution. So du1 over dx1. Meron ba? du1 over dx1. 0. Wala namang x1. du1 over dx2. 0.5. du1 over dx3. 0. Wala namang x3. And here, du1, x1. Wala namang x1, x2, and x3 dito. So everything is 0. Okay, gets? Gets naman? Gets? Okay. Sige. Now we proceed. Now we define the infinitesimal strain tensor. So the infinitesimal strain tensor is just described by this one. Now we will see later ano yung physical significance nito. So one assumption in infinitesimal strain tensor is that there is no large deformation. Okay? So what we just study here in your undergraduate courses will mostly be just small deformations. Okay? Since bihira naman kayong makakita siguro ng large deformations. Okay? So, yan. Infinitesimal strain tensor. Okay, so that's the formula. But what I want you to know, or what I want you to get from this lesson is ano yung significance ng formula na ito. Yan. So let's see. Ayan. So if we just expand the infinitesimal strain tensor, what do we get? So we get this, no? Gets ba kung anong nangyari from the previous slide? So the previous slide is this one. 1/2 dui xj uj xi. Okay? So what happens pag dito? So here, I equals 1, j equals 1. Okay, let's just annotate. Here 1. I equals 1, j equals 1. Okay. So ano nangyari? 1 half times du1 over dx1 plus, so ano nangyari? 1 half du1 over dx1 plus du1 over dx1. Since parehas lang naman. So we get this d1 over dx1. Okay? Now here, for example, kita nyo naman, no? du1 x2 to x1. So ano yung significance nito? Now remember that strain, okay? Strain in your solid mechanics, in your ES102 is equal to the deformation, deformation over the original length. Tandaan yan, deformation over the original length. Now this deformation right here, this is normal strain, no? Normal strain. Ayan, yan yung deformation, di ba? This is U1. This is the displacement of the point. Ibig sabihin yan yung deformation. The original length, okay? The original length is this. The material description. Kaya original length yung ginagamit natin dun sa ES102. Why? Because we're using the material coordinates. Okay ba? Kaya original length. Ayan, oh. Balik tayo dun sa previous slide. Ayan, this is the original length. Hindi natin ito ginagamit. Okay? Ito yung ginagamit natin. So yan yung significance ng formula. Now, for here, yan, note for non-diagonal elements, the engineering shear strain is equal to 2 epsilon ij. So 2 times the component of the infinitesimal strain tensor. Sige, balik tayo doon sa ES102 nyo. Just notate. Ayan. So for example, we have this object. Ayan. And then, okay. And then it deformed like this. It deformed like this one. So ano yung epsilon ij nyo dito? Wait lang ah. I think I have a better illustration. Yan, may illustration pala ako sa ube. I'll just show you. Ayan. So here, we have the normal strain. So DUI, okay, DXI. So this is the displacement, okay? This is the displacement, this is the original length. here in the shear strain, ayan, shear strain, ang shear strain natin is defined by the change of angle. Ayan, change of angle of the original thing. Okay, so ano ba yung change of angle na yan? So from 90 degrees, di ba naalala nyo dati? Kala nga, natatandaan nyo pa ba yung ES102 nyo? Shear strain is equal to like 90, which is pi over 2, minus the change of the angles. Right? So this one is the theta. It's the new angle. So 90 minus theta will be the shear strain. Now what is that? Ayan o. This one is this one, and this one, this angle is actually dui over dxj. This angle is duj over dxi. So is that equal to d? Okay, dui over dxj plus duj over dxi. That's it, no? 90 minus theta, okay, is just equal to the sum of these two angles. Ayan. That's why, kung yung epsilon mo, epsilon, ayan, ang definition nito is 1/2 of this one, of this thing. Okay? Then, the engineering shear strain is 2 times the epsilon ij. Okay. So, yan yung mga things na dati nagkakamali ako because I think it was not explicitly noted, hindi na ingrained sa mind ko. And then when I tried to program things, I tried to program things, ayun, nagkakamali lagi ako. And this was it. Ayan yung pagkakamali ko, no? So, 2 times pala siya. So, I guess that's very important, especially if you're trying to develop some numerical modeling. Ayan. So, dyan ako dati nagkamali. Okay ba? Yes? No? Okay pa kayo? Okay. Sige. Yan. Ayan. Also, this infinitesimal strain tensor is second degree tensor. Okay? It has a degree of order 2. Okay? Second order tensor. That's why it will have the strain transformation. Okay, the strain transformation, the same with the stress transformation. Okay? So same lang ng transformation ng stress. That's what I'm saying. Okay, now we have this recap of our class today, synchronous meeting. We have discussed material and spatial description, and then noted that the advantage, it is advantageous to use material description for solid mechanics, and for fluid mechanics, it is advantageous to use spatial description or the Eulerian description. Okay, and then we describe the displacement gradient. Okay, or how much does a piece of length deform along its length? Okay, and then we discussed the infinitesimal strain tensor, and noted how it is compared to your knowledge in ES102. And then we discussed how strain transforms. Basically, it just transforms like stress because it's also a second order tensor. So I hope you remember how to transform Kaya ng ginawa natin last time. And then for the principal strain, yeah, we just glance through this because I think I will just repeat on I will just repeat on discussing principal stress again because it's actually just the same. Okay? The same as the stress tensor on the transformation laws. So parehas lang din ng pagkuha ng principal stress. Okay. Any questions? Clear naman or at least medyo okay. Okay. Sige, walang questions. Sige. Um, so next meeting, we're going to discuss the last topic for continuum mechanics, which is the um, constitutive equations. So basically, we're just going to discuss way one way to relate stress and strains, which is the Hooke's law. It's very important. Si Hooke's, yung Hooke's law, si Hooke, Robert Hooke, in mechanics. So we're going to discuss uh, his uh, contributions. Okay? Sige. Wala nang questions talaga? Wala? Okay. Ayan. So before going and having your breakfast, please answer. After answering, you may go. Good morning. You guys, thank you for attending. Uh, Happy breakfast. Good morning.